Hello, everyone. The title slide for our presentation today is a festive one because I'd like to congratulate you that we are actually on the last lesson containing rules of inference. So in this lesson today, you will learn the last two of the many rules of inference. So let's get on with it then. The first one is called transposition. If you're given any implication, you can actually switch the places of the antecedent and consequent to arrive at still another implication. But to do that, you will have to change the signs of each one. Going back to the illustration of the piñata from which I began, perhaps you can say, if the girl hits the piñata, then the candies will come out. It's the same as saying, if the candies do not come out, then the girl didn't hit the piñata. For A implies B, it's the same as not B implies not A. But let's explain this a little further. Perhaps it would make sense if we will try to remember modus tollens. Okay, so here is transposition once again. A implies B can be transformed into not B implies not A and vice versa. Let's begin with the left hand going to the right. Here is a formula for modus tollens. A implies B. If that's given, and it's also given that it's not B, then you can infer not A. And it seems, okay, that if indeed I have an implication, if I negate the consequent, I will get the negation of the antecedent. That's how modus tollens works. But going further, you notice that modus tollens is also trying to say that it must be not B implies not A if you have A implies B. Thus you arrive at saying, okay, if you say A implies B, I guess you can also say not B implies not A. Now let's go then from right to left. Starting with not B implies not A, if you negate the consequent, you also end up negating the antecedent. And if you say not B implies not A, looking at the formula for modus tollens, you can say, oh, then perhaps I can also say that A implies B. The other thing about transposition is that it can actually do in one step what takes material implication 2 steps. So imagine that we haven't learned transposition yet. If you're given A implies B, you can, by material implication, change that into not A or B. So remember, in material implications, the antecedent that changes the sign, the consequent remains the same. And then if you're given a disjunction, like in this step over here, you can choose any element of the disjunction to be your antecedent. And if you want to do that, then you'll have to change its sign. To make B the antecedent, it has to become not B, and then not A remains the same. So you can go from A implies B to not B implies not A by doing material implication twice. But the advantage of transposition is that you can do the same thing in one step. A implies B can simply be transformed into not B implies not A. So let's try then to apply this in a problem item. So let's take a look at what we have here. Given X or Y, given not A implies not X, given not B implies not Y, given A or B implies C, we'll try to prove C. Now, working our way backwards, because there's no single letter in the given, C will lead you to A and B. A and B have something to do with X and Y, and you have X and Y over there. And perhaps you think, if only X were the antecedent here, then maybe you can get A or B by way of constructive dilemma, so that by modus ponens, you can get to C. But somehow you can't do that yet because X and Y are consequents over here. And so perhaps, as you may have guessed, transposition will help us do the job. If you start with not B implies not Y, you can turn that into Y implies B, and then follow it up with not A implies not X, and turn that into X implies A. Again, remember, you still end up with an implication, but the elements change their positions and also change their signs. The antecedent becomes the consequent, and the consequent becomes the antecedent. Now that you've switched their places, now X and Y are antecedents. All you need to do next, I guess, is to bring back Y implies B from above, then put the statements together by way of conjunction. Now you have X implies A and Y implies B, the first statement you need for a constructive dilemma. And then you need the disjunction of the antecedents. It's already given here, X or Y. So by way of constructive dilemma, you can now infer A or B, because the letters A and B are the consequents in the conjunction above. The consequence of the implications in the conjunction above. And since I have A or B, I can now simply use modus ponens to arrive at C. Okay, that's one way of applying transposition. Going further, let's now talk about exportation. If you have an implication where the antecedent is a conjunction, you can actually turn that into an implication where the consequent is an implication and the antecedent is a single letter. So if you read this, you can say, given A and B implies C, I can also say that A implies B implies C. Maybe it will be clearer if we give a few examples. What is your favorite drink? Well, one of my favorites is, of course, root beer float. What do you need to make root beer float? You have to have ice cream and soda. Or better yet, vanilla ice cream and root beer. You can see it here, okay? You have to put together ice cream and soda so that in the end you will get root beer float. It's the same as saying, begin with ice cream and then take another or wait for another condition. If you also add in the soda, then in the end you will get the root beer float. Maybe at this point you notice that the form on the left simply gives you how the so-called ingredients are put together, whereas the form of the same statement on the right gives you a more chronological sense. Begin with one, add the other, and you get the result. Over here, put the two together, and you get the end result. But they mean exactly the same thing by way of exportation. Or perhaps you could take another example. You're the type of person who would say, if I have a birthday cake and presents, my party will be complete. So the completeness of the party is dependent on these two elements. You have to have cake, you have to have presents. If only one, then the party will not be complete. It's the same as saying, okay, the cake has arrived. Then you tell yourself, okay, party is not yet complete. There's still something missing. You still have to wait for another condition, because what's the other condition? The presents. But when the presents arrive, since the cake is already there, you can already say that, okay, now at this point, the party is complete. On the left, put them together, you get the result. On the right, take one, add the other, and you get the end result. That's how exportation works. And remember, it also goes from right to left. If you're given the statement on the right, you can change that into the form on the left. Now let's take a look at the problem item. And perhaps if we will imagine that we have not learned exportation, this is going to be a sample of how you may want to prove it. So you can begin with X and R implies M because you have not M here as a single letter. You know, you can't use X because X is somewhere. They are elements of conjunctions that happen to be part of a bigger implication. So perhaps we will begin with not M, okay? And the only statement that has M is X and R implies M. You get this by modus tollens. X and R becomes not X and R. And then you have the not sign there. You can bring the not sign in by De Morgan's rule, but of course, change the conjunction into a disjunction. So you get not X or not R. This time you can bring in X, and by disjunctive syllogism, you arrive at not R. Okay, keep that there. Work on another statement. X and I implies R. Since you have not R, you get not X and I by modus tollens, which can be turned into the disjunction not X or not I by way of De Morgan's rule. And since X is given, you can get not I by disjunctive syllogism. And then go to X and H implies I, do the same thing, okay? You have not I there, and so by modus tollens, you get not X and H, which can then be translated into not X or not H by De Morgan's rule. Since X is given, then you can then arrive at not H by disjunctive syllogism. But perhaps another proof can be written by way of exportation. So we're still on the same problem. Let's begin with X and I implies R. You know that you can change this into X implies I implies R because you wanted to isolate X because X is a single letter here, and immediately you can use X to get I implies R by modus ponens. Okay, do the same thing for X and H implies I. That's given. And then use exportation to make X the single antecedent, giving you X implies H implies I by exportation. Then since X is given, you get by modus ponens H implies I. You now have H implies I, you also have I implies R. Maybe you can use them so as to arrive at H implies R by hypothetical syllogism. Then next, we haven't worked on the third given yet, so that's where we go. Let's work with x and r implies m, that's given. By exportation, you isolate x as a single antecedent, x implies r implies m, because you have x as given, so that will then lead to r implies m by modus ponens. And since you have not m over there, okay, you can go to h implies r above, okay, to turn it first to h implies m by hypothetical syllogism, so that from not m you can get to not h. How will that happen? You already have h implies m over here. All you have to do now is to add not m, or to put down not m over there, and you get not h by modus tollens QED. The same proof can actually be written in this way, where you can actually make it more simple. So tackle all three all together. So it's x implies x and h implies I, x and I implies r, x and r implies m. And then all of them you shall change by exportation using x as the antecedent. So x implies h implies I, x implies I implies r, x implies r implies m. And since you have x as given, you can now use x for modus ponens because x is the antecedent of all three. You end up with the consequence of each one. H implies I implies r implies m. And then do hypothetical syllogism, I implies m. Okay, remember, you have to work with just two statements from above it, directly above it. And after you get I implies m by hypothetical syllogism, bring back h implies I, so that using I as your middle term, you get h implies m. And same as the earlier proof, you now use the given not m to arrive at not h by modus tollens. Quod erat demonstrandum. So try to tackle all of the other exercises for the rest of the lesson, and congratulations again for finally learning all of the rules of inference on our list. As usual, have fun with the exercises. Thank you.